Yeah, thanks everyone for coming. I'm really delighted to be here. And also thank you, Professor Ima, all the committee members to have this wonderful chance. I was a little bit nervous yesterday. I went to this science fair thing. Like was seeing everybody was wearing suits. I was told this is must, like in Hong Kong. I didn't bring any suit, but sounds like today it's a little bit relaxing. Um, so that's good. And you can interrupt me anytime. I feel like it's more like a very kind of relaxed place, and we can talk about engineering science and then with fun. Okay. Sorry, this first time I'm looking at the screen in front of me to talk. I'll try not to look back to the screen. Okay, so the topic is always still Bayesian, so big models. I'm trying to touch base the history and discuss the current and look more into the future. Although some old generations, we probably were born as a Bayesian or to some degree, especially in statistics, but I try not to be too obsessed with some traditional kind of disciplines. But let's see what happened and what's going on, what might be the future. Okay, my name is Zhuowen too. I'm from UCSD. All right. So I'll have these four basic items to talk about. And again, you can interrupt me anytime. I'll quickly go through some Bayesian statistics, Bayesian overview, and talk about some old, kind of relatively kind of adversarial learning-based kind of things, starting from the Bayesian theory, and then touch on based on the recent diffusion models and how do we put back Bayesian statistics, all these things, and also trying to talk a little bit more about explicit kind of models with controllable image generation. Okay. All right. Quickly, Bayesian. I assume everybody in the room is familiar with the general Bayesian theory. And so in general, when we look at the problem, we look at the input. Here is a high-dimensional space, RQ, and then we look at output space, Y. If it is a structure prediction, then more or less it's a sequence. If it is binary, then it's plus minus or multi-class. This is a famous picture of Bayes. All right, okay. So this is kind of the very basic formulation. Y is the output, and we're given X, and then we study the posterior and can be decomposed into the joint distribution and the X. And then you can further expand with prior and likelihood function. So this is the basic Bayesian inference where you look for the maximum Y that maximize the likelihood and plus the times the prior. You can drop X because it's shared for a given fixed X. Okay. All right. And this is a very basic illustration. When I was a student trying to understand why do we need a Bayes, right? If we just look at the equations, sorry, how do I go back? Okay. If we just look at the equations here, sorry, it's a little bit delay. How do I move back? So this cursor moving back, but it's not going back. So should I move back? This one. No, this is move forward. I want to move back. Okay. Okay, now it's good. Okay, thank you. So if we only look at these equations, it's very abstract. But some examples can give us a little bit more kind of intuition, right? If we look at the input as data, just X, here is two-dimensional, not three-dimensional, just two-dimensional if it is X. Then the white space compose a lot of possible 3D here shapes or objects that can possibly produce this image X, which is projection from Y to X. And then the basic Bayesian solution says, now if we study the likelihood, what are the possible shapes or objects that can generate this particular projection, X, which is in two-dimensional. These are three possibilities, for example. Then in the likelihood, they are equal likely to generate this 2D image. And however, we can utilize a prior to see the top two shapes are very unlikely to appear in reality. And then we can put the prior distribution on top of these three possible objects, then multiply with the likelihood, then in terms of inference, we obtain py given x. So that was a little bit like the basic baby statistics we were told as a very kind of a motivating kind of thing to use in inference. So how much time until when? 35 until so from now. Okay. 30 or 35. Okay, 30. Okay, all right. Thank you. Okay, so I'll try to. So basically, in early development of computer vision, the objects, I'll speed up a little bit. In early development of computer vision, the objects in study are often simplicity from relatively small scale data sets. So the top-down part, again, can therefore provide a very strong regularization and so-called inductive bias to the bottom process. So it almost become natural to use the basis theory. So when I was still was interesting, I still remember the first paper I submitted to CVPR, where I put the simple Bayesian formulation, and 2 reviews out of 3 said, oh, this is very novel because they're using Bayesian to study computer vision. So that was kind of interesting moment. And then, so my early work with my advisors, collaborators, so we built up the so-called image parsing, and with a data-driven process to guide the it's not. To guide the so-called top-down process, then you can do splitting, merging, and diffusion back then. But back then, diffusion amounts to the change of the object boundaries, things like that. All right. So that was kind of earlier work, and then the spirit is that you can use the data, use the top-down prior to guide the bottom process. It's not, it's kind of so hard to use. Sorry. Okay, so back then, as I said, using Bayesian was a very intuitive. And if you were, so by the way, so how many of you have seen this picture? There's a, okay, not too many. So it's kind of lost. Anyways, so that also reminds me I'm too old. But anyway, so basically, when you study an object like that, if you study shape and face, now everybody goes through Gautier kind of thing. Face recognition is just by default. But even 15 or 20 years ago, it was not that easy at all. So if you would study shape motivating example to think, okay, so how do we study face? We have to have mostly 2 eyes, nose, mouth, that they are symmetric. Then you put some spring over there, then you can put things together. Then these are strong prior that can use. Otherwise, like where are the constraints, right? So this is kind of the motivating example, and because of that, then you can naturally, include these priors. And then later on, and then from a sequence of all these works and with the different researchers, and this is like Sevilla and Feifei, their work, and to put some latent derivative models on top of parts, then backwards models start to emerge, then by putting the prior to regularize them. So basically, what I'm trying to say is that the very basic fundamental Bayesian theory makes sense. And also early works and trying to leverage some of the data-driven techniques together with some regularization on the output space also makes some sense. And also, let's look at, since we're talking about generative model a lot, now let's look at some earlier motivating examples in terms of generative models. Any chance we can switch? So hard to use, sorry. Just not. Okay, I see. Okay, so basically this, if we look at an image like this, This is like a very groundbreaking work from Bergen in 1995, which has been almost one of the most kind of fundamental guidelines in terms of producing a generative model, which we now, like everybody is familiar with it, all these just text to image, text to video, all kind of things. But the very basic fundamental idea from Bergen essentially is to say that if you want to study an image here in texture, because in 1995, studying a generic pattern is very difficult. So people utilize texture as a test bed to illustrate statistical methods. So basically, suppose if you look at an image I, and how do you say you can reproduce a similar image? Then the idea is that you want to define a few sufficient statistics. And then if you would define a few sufficient statistics, and then if you can match the histograms from your synthesized image to your input image, then you say you're able to capture the underlying kind of essence about your input image, which is a texture here. And back then, there's no really statistics, really formulations on top of that, but the idea saying that matching statistics from a generated image to the input image can lead to the capture of the underlying statistics. Actually, that concept actually lives almost forever. And then what they did was they initialized the image, let's say Gaussian. Instead of having any explicit procedure, they do so-called histogram stretching to turn an arbitrary Gaussian image to a synthesized image. That was no diffusion process, nothing. It was just a simple deterministic procedure to map your input I0 prime to your I prime. And then when the statistics are matched, they say, okay, boom, you have it. So that's kind of the fundamental idea without, again, any explicit statistical models on top of it. But underlying thing is trying to minimize the distance between your input image and your generated image. Again, as I said, this idea still lives today. And later on, Zhuowen and Mumford turns that into more a statistical formulation such that then you can have a really explicit model now. So that's kind of the really a fundamental kind of a motivating guideline. Okay, so yeah, I'll try. So this is a simple kind of line, a few lines of code, like a Python I wrote. And then, let me see. Oh, sorry. Can you click on the image? Back. Can you click on the image? Yeah. Okay, so these are the images that are generated from a few lines of code. I think this is a very motivating example. If you start to get into imaging or computer vision or generative models, I feel like this is something probably we really want to keep in mind almost all the time. So what happened, I'm trying to show is, suppose this is an image of 500 by 500. If you have these few lines of code, and Earth has roughly 4.5 billion years of history. If anybody here is lucky, you carry your laptop and taking a time machine to travel back 4.5 years, and back then click a button to say, boom, you start to see these images. After 4.5 billion years, suppose you see, let's say, 60 images per second. For 4.5 billion years of history, the chance that you see any pattern, any particular image or tree, and like a dog, any particular pattern that look like is 0. So what I'm saying is, even you constantly see image like this, then the chance of seeing any meaningful pattern out of this 500 by 500 images is near 0. So the basic fundamental image manifold is exceedingly small in this potentially possible, all possible images. Here, suppose you have 500 by 500, then the possible images you have is essentially, if you have RGB, then 255 times 255 times 255 to the power of 500 by 500. So that's the extremely large number. So any modern generative models we are able to have to show that we are produce all these cheetah, dogs, faces, kind of things, extremely challenging. So that's what I want to say. And the underlying kind of statistics in terms of building the generative model essentially boils down to the match between your so-called empirical distribution and your model distribution. Basically, you define a few features, HI, and then you want to have empirical statistics collected from your training set to match with your model statistics. That is an average, essentially, out of the images you can synthesize. So that's kind of the underlying thing. I'll try to be a little bit fast because of the time. And so this is kind of a basic illustration so to talk about the difference between generative model and discrete model. So for example, always an example I want to show is in terms of understanding generative model, it's almost like if you come to Hong Kong, you can immediately speak Cantonese. Then you have a generative model. And then discrete model says, can you differentiate between Cantonese versus English or Cantonese versus Italian? So in general, discriminant model focus on the classification, where the general model focus on the produce of the full statistics, essentially, to some degree. And so as I said, almost 99% of the previous kind of principle in terms of producing generative models before then was trying to build a model that can match statistics. So this was like in 2007. So I was thinking, so gee, can we turn this thing around? Instead of having those manually designed features, HI, that was really hard to generalize back then, can we turn that criteria into something that's more objective? So this is a very basic Bayesian rule. Suppose you have target plus y is 1 and minus is just minus 1 just background. And then this is simple posterior distribution py plus 1 given x. Then simple Bayesian. In the end, you can obtain this the formulation. And if you further let's say simplify, assuming equal prior on the positive and negatives, essentially you can obtain this very interesting kind of formulation. What I want to say is, suppose, let's say, you want to speak Cantonese, and then the condition is you want to speak Cantonese. Then every single x is one sentence out of your mouth. Essentially, what this equation says, if you want to speak perfect Cantonese, then as long as, let's say, you can speak perfect Italian, let's say, and also you have a model to tell you whatever the sentence or the word are coming out of a math, how likely the ratio between how likely it is Cantonese versus Italian, then you can speak perfect Italian without studying Italian and Cantonese at all. So basically, it's like if you have a reference model and then you have a discrete model ratio, then you can immediately turn yourself into a generative model that can produce almost anything and that it is a target. But however, this is a chicken and egg problem. You want to speak perfect Cantonese, you need to have a capability to speak perfect Italian and also a ratio to say how exactly it is Italian and also Cantonese. So then, and back then, I turned this into like a recursive procedure, starting from reference distribution. Now, once I show you the slides, you will see what's going on. So basically here, the red points are all these are the given ones. So every single red point here represents a Cantonese sentence. You can start from this random distribution, let's say Gaussian, and then you can learn a discriminant model to separate the Gaussian from the Italian, Cantonese. Then you basically highlight the boundary. Then next step is to learn the adversarials out of it. Then sequentially, if you do this, in the end, your adversarials are not separable from your target Cantonese, then you can start to speak perfect kind of Cantonese. So that's kind of a thing. So essentially start from Gaussian distribution, very much like a modern diffusion models. Then you sequentially learn, update. So that's kind of the basic formulation because, again, I don't want to spend too much time to talk about this. So essentially, this gives us a fundamental energy-based generative adversarial models. And also back then, I was showing this texture modeling, image classification, and learn Van Gogh style and do to style transfer and natural image statistics learning and use this to do noising and also do some face modeling. And so this pretty much gives the very much the basic foundation for modern generative adversarial learning. Of course, this is energy-based. I was implementing using boosting because this was 2007. And later on, so this idea has been followed by generative adversarial neural network people by realizing this in a neural network setting. But the very basic kind of formulation pretty much was there. But of course, there's still some difference because they have explicit separate generator, discriminator, things like that. But the fundamental foundation has been laid out over there. So that's kind of another way of thinking about Bayesian statistics to in the end to lead to the exploding development later on generative adversarial learning. And also we had another work afterwards to build this thing on top of neural networks about what we call the introspective neural networks. Okay, all right. So let me go to my point. So that was kind of the Bayesian kind of thing. So yeah, so kind of it. Okay, all right. So sounds like early times we really enjoy Bayesian and like actually resulting a lot of kind of academic work and also industrial work. But why is Bayesian not any more widely adopted recently? So this I want to show you another work of mine, kind of that was not Bayesian but still motivated from Bayesian. Yeah. Okay. So the basic idea is to perform a so-called structured prediction. Here, the idea is to say if you see a horse image, you do a very simple task, trying to label every single pixel on the background and also horse image. So for any pixel that is on the background, it's let's say 0 or -1. Any pixel that's on the horse, then plus. We do just a simple this now called the image labeling. However, if you only compute the local features out of it and trying to perform a classification, the task is challenging. Suppose you only perform patch-wise classification, then you obtain, let's say, a classification map like this. However, if from the classification map, from your first classifier, at every point, you shoot out all these rays. So all these blue bounding boxes or these boxes are the possible kind of probabilities you can poke to utilize. So basically, in the end, essentially, you do a second round of classification by adding the features of this image pattern together with the probabilities from previous round, then train another classifier. You can see, so these red ones are the high weights of those areas to poke. And then if you train next round of classifier, then you will able to see the map. Yeah, okay, thanks. So the map has been, you can see, lot kind of enhanced. And if you do this recursively, in the end, you will obtain a map. Oh, okay. Oh, I see. I should point that way. Okay. Okay. It's okay. No. Maybe just give me the laptop. What can you put the laptop there? I can just click on the enter. That probably will be easier. Okay. And the mouse is good. Yeah, mouse power is good. Yeah. That's okay. Yeah, I think that's good. Yeah, this is good. Yeah, okay. Yeah, sorry about technical. So you can see recursively, if you do this multiple rounds, in the end, the segmentation map, you can see, or labeling map, has been significantly enhanced. So this is kind of a very simple strategy, but actually it represents essentially, shameless to say, a groundbreaking work. Because previously, we have been studying context. Up to that point, in machine learning or computer vision, people have been focusing on, let's say, hidden markov models or conditional random fields or marketed random fields with a neighborhood only 2. Why? Because once you have, let's say, 10 neighborhoods, the search space explodes. The thing is, it's now a widely realized concept that making a prediction for multi-class, for example, 50,000 predictions of large dimension feature, is even you have 50,000 classes. If you have a feature dimension of 10,000, nowadays it's nothing. Right? So we have been using all these ChatGPT, all kind of thing. If it has a dictionary of 500,000, then it's a 500,000 soft mask classification task. A feature size of 10,000, it's nothing. However, if you have a window, let's say, of just 20 length, a binary classification, the search space is 2 to the power of 20. And then if your window size is 1,000, even a binary classification boils down to a search space of 2 to the 1,000. That's an extremely large space. So we have actually, can you move backwards? Yeah, back, one more slide, back. Yeah, here, yeah, okay, thank you. So basically, this gives a new way of including context into prediction. That has increase of a context window previously in 2 to 3 to orders of magnitude. If you have 1,000 images, then to 1,000,000. So essentially extend the window size from 2 to 3 to 1,000,000. And this has been adopted as one important step in AlphaFold. Of course, I was weeping tears, cried for a whole night after I learned that this AlphaFold has been recognized as a Nobel Prize winning work, but my name was not included. But I'm joking. But I'm glad to see a work like this has gone beyond the machine learning, had to make a huge impact to science and beyond. And then since then, shamelessly to say, after the auto context work, the scope or the size of window that had been used to do structured prediction has been significantly enhanced. Now, large window actually has not been a problem of a contextual window. Because of time, I don't want to talk too much about that. And then you're welcome to talk to me or read the papers. But essentially, in a way, if you even look at that auto context map, even it has something to do with attention mechanism in transformers. Essentially, it is doing some kind of attention from your current pixel to all possible pixels in that particular image by turning a search string into a classification. So that's kind of how you can see things are happening. But this is still kind of a bottom-up process. So now let's come back to the main topic. How do we bring back Bayesian? So you can see, right, fundamental Bayesian statistics led to, again, modern exploding development in generative adversarial learning and generative modeling, and also to shape up the inductive bias in putting into some early kind of statistical modeling. But what's wrong with Bayesian now? So why we don't see almost at all any specific papers talking about Bayesian in Europe, CVPR, ICCV, all kind of thing. And then most kind of the works are now data-driven. I think I summarize into a few kind of items. First is the rich features that learned from large-scale data become substantially more robust than manually designed ones. And the priors have been more or less included in this bottom fashion from X to Y, and an explicit, a separate prior is no longer that needed, or it's harder to be incorporated directly into a modern, let's say, a data-driven or deep learning principle. For example, if you have, let's say, an edge detection method, or you have object detection, kind of how do you put the prior over there to combine these two routes? It's not necessarily clear to us. So now coming back to modern diffusion models. So what is the difference between diffusion models, the fundamental statistics, or stochastic modeling computing mechanism that we also engaged 10, 20, even 50 years ago? So I would make an analogy like this. So suppose, let's say, you want to come to Hong Kong. For me, from San Diego to Hong Kong. For the rest of you, like maybe you're local or everywhere. And if you decide to come to Hong Kong, so if you're born as a traditional statistician, your idea is that in order to plan the trip or understand how to come to Hong Kong University to attend this wonderful forum or symposium, then you have to know where Hong Kong is. And also you have to know where you're living in or staying. And then you're trying to see where will be a viable route from, for example, me from San Diego. Oh, thank you. From San Diego. It's a little bit unfair because of the technical. I'm joking. I can talk about that without the screen. So the motivating thing is essentially trying to draw the map. But we all know early times, right, to have a precise even map of China or any country, it was difficult. It is difficult, right? So we saw these movies, all kind of things. So Japan invaded China, like a long time ago, but essentially we saw later on, realized essentially all these Japan troops, like they carry like 1,000 scale maps, essentially are even more accurate than the maps the Chinese military kind of had. So essentially what I'm saying is like to produce a map is really challenging. And then the diffusion model in a way turns the thing around. So instead of having a map to exactly know where Hong Kong is, and then we essentially can, let's say, come to Hong Kong University without knowing where it is located on the map. By, let's say, after 1 hour, let's say go, let's say to this, let's say I'm just making up, to northeast. And then essentially, as long as you know a few stops, and you know how to move next, you don't need to know exactly where Hong Kong University is. Although we do in the morning, I was walking. It was really challenging to come by walk. Even I have Google Map. But essentially, all we need to know is need to have essentially are a few directions to tell us, and without the need to know exactly where Hong Kong or Hong Kong University is. So what I'm saying is the diffusion models, instead of the need to know where everyone is located on the map. As long as you know how to move, then if you are able to capture or cover the entire space, then that's good. So that gives us like a significant lift in terms of modeling capability. That takes us to what we are now. So what I promised you to talk about the current, what I'm saying, the explosive development diffusion model, why the statistical foundations have been so advanced or capable than before. Now we actually are shredding the burdens on knowing every single thing in terms of its distribution and all these explicit model, to the degree that we only need to know how to go. Just like now, is like if you go to any major cities, like I was living in Beijing for a long time, but back then it's like all these taxi drivers, they can drive, they know where are by memorizing some historical landmarks. Now, like if you go to Beijing or Hong Kong even, and a lot of the drivers don't know where they are, so they just put the address into the map and then Google Map or whatever the map it is, and they take us. So essentially, I think that's what diffusion models are doing for us. So I'll speed up, sorry. And so this was a work we had last year by introducing explicit priors back to the diffusion bottom-up diffusion process, such that now the priors or the base can come back. So again, in the interest of time. So these are some top-down models we learned for the shape only. And the procedure is the following. Suppose the traditional Bayesian kind of prediction, you have the observation, any point over here essentially is x. Now, given this x, we can obtain its possible y's using the prior and also the likelihood. Then in the end, we can combine the two together to the formulation. The stochastic gradient Langevin is by essentially having the probability distribution first, then trying to compute the gradient. In terms of a diffusion model, the Bayesian diffusion model we had, essentially we have two parallel paths. One is the diffusion model for the prior, and another one is diffusion model for the data-driven. And once in a while, you can utilize the diffusion prior diffusion model to explicitly step into the data-driven process to do the merging or guidance or refinement. Then after the merging, they will actually parallelly run, and they merge again. In the end, you will have a decomposed process in which the prior diffusion process and the data-driven prior diffusion process has been explicitly studied. And we compare this to, for example, widely adopted the model classifier free guidance, where the prior part and the data-driven part has been mixed all together in all more or less a very black box way of training and learning. We show that this type of explicit Bayesian diffusion model can bring back a lot of improvement and also transparency for this single image reconstruction, which here Professor Jiajun Wu did a lot of early work. His MARNet, all kind of thing. We use his MARNet a lot earlier in some other works. But nevertheless, essentially, I'm trying to kind of give out some reasons why Bayesians were popular, why it's kind of a little bit lost, and then there's a chance to bring them back. Okay, so I have 1 minute left. I'll show you some of our recent work that we're trying to push through the explicit modeling, and by doing controllable image generation. And also, we talked about the generative model and discrete model. There's this interesting thing I want to share with you. This work we post on arXiv. And regardless how wonderful the modern image generation models are, all these kind of CNN-based and these VIT-based, all kind of thing. DITU, VIT for image. And if you would, even they are hard to distinguish from your naked eyes. If you train a classifier to separate the real versus fake, the convergence is extremely fast. A few epochs, immediately you can separate. So what I'm saying is, no matter how good your generative models are, the fundamental statistics are still very, very different. But for a lot of generative models, the purpose is not to trying to be exactly same. As long as they can fool our eyes to some degree, it's good enough. So we can still utilize these generative models to produce some images. So we did an interesting kind of analysis. And this is for the first time, we're showing mathematical equivalence between your real versus your generated data for your data augmentation task to see, say, how many copies of real data is equivalent to how many copies of synthetic images if you were to use them to enhance your classification detection. So we didn't do detections, I'm just pointing to the future. So essentially, although there's still fundamental difference between the real versus synthesized can use us to guide a lot of the Lexi vision or tasks beyond. But you always need to spend significantly more amount of synthetic data to help with your task versus your real data. There are a lot of these plots in terms of the equivalence we showed. You're welcome to read the paper. So then I quickly say a few words. Then recently this is our ICCV paper that we particularly like, and actually Sainin talked about image generation yesterday on the Science Forum, and essentially nowadays trying to explicitly control the number of generated objects is not easy. And we came up with a pretty smart method we call the coordinate map. So instead of having a classification map, we turned this into a YOLO type of thing. So each cell would produce the portion of a particular this area to the current object. So that way, if we sum up every single cell, that is just the total amount, the number of basketballs we have. And this is fully differentiable. So this is differentiable object counting that can use to control image generation compared to previous density-based kind of thing. We show significant improvement. So not only we are able to obtain state-of-art results in terms of object counting, but we are also directly you can utilize this to control the number of objects you can generate, which is fully differentiable. And also, this is another work of ours, like ICCV, way to do text to layout and layout image generation. It's a layout control kind of thing. That is also another way to introduce your top-down information to control the image generation. And also, we have an upcoming NeurIPS paper studying the layout in terms of with the layout, how good the images are. The general take-home message is, nowadays, regardless how good the generative models are, if you have layouts that are very kind of overlapping, all the recent models are doing poor jobs almost. And also, there are two types of overlaps. There's these area-based overlaps, and then there's semantic level overlaps. If they have strong overlaps, both in terms of semantics and also the area, the result image quality is always very poor. So essentially, there's a long way to go. So let me quite quickly summarize. Essentially, so I promise you, I talk about a little bit kind of older history and also the current. So in the future, I agree with Professor Yima and also a lot of other people are saying in terms of we need some experience model, things more interpretable, but we don't want to go back to the previous pitfalls where we're absolutely obsessed with everything being Bayesian type of thing. I think that time of these efforts, they are gone. It's very hard to directly combine prior or like with likelihood and say, oh, boom, you have this experiment model. We have to utilize Bayesian or these experiment models in the right way, at the right time, in the right form to make a difference, to make a practical difference, and hopefully also theoretical significance. Okay? All right. Thank you so much. Sorry about the technical problem. Yeah. Okay. Thanks.
I think it gives us a new and insightful perspective on series from the theoretical perspective of generative models. So any questions from the audience? Yeah.
So yeah, good. Honestly, I have a I actually like the topic perspective connecting to the Bayesian inferences. In fact, my view is that a little bit more extreme than you. In fact, the diffusion model, everything you said here is exactly within is still very much precisely in the Bayesian framework, right? We learned the distribution that which is prior. Although now the distribution is represented in through the data, and maybe access to a diffusion model. I like your example about you're trying to make a point of how do we get to Hong Kong, right? To make an analogy with diffusion. I actually gave in my course I talk about this. There is a phrase says all roads lead to Rome, right? So think about why. This phrase actually captures exactly the diffusion denoising model. Why all roads lead to Rome? Because at one point Rome conquered the whole world and they build roads to the rest of the world. That's a diffusion process. Hence,
that's an excellent point, yes.
Yeah, everybody just follow the road. You don't need to know the map. You will get to Rome eventually.
Exactly. Yeah, as long as you identify a few landmarks, that's exactly like these.
Follow the roads.
Yes, yeah.
Which is exactly the path. So, I mean, by the way, the whole thing, all the conditional, you said that we condition on the observation, single image generation, and also combined with the diffusion process, which is exactly actually using the prior you learned from the diffusion denoising process. So in a way that honestly, this is actually was also summarized in our recent new book that in fact all the practice these days with the generative model are very much in the context of same old Bayesian framework.
Exactly.
Yeah. Thank you.
So yeah, thank you, Professor Imad. So that's a great point. So essentially, again, my point is like history is worth.
It's a slightly different test, but it's still spirit the same. Yeah.
But now we want to advance the science. We probably also don't want to be too obsessed with all the kind of discipline, but put them into a new perspective, and that is aligned with the modern development and just move on, right? So just by focus on fundamentals, but also need to focus on compute, all these large-scale computing, computer scale kind of things. So as long as we can combine these two types of kind of thinking and bearing these things in mind, I think we can advance science, both science and engineering. So again, I was really lucky. I was really happy to see that my work has been in part of a Nobel Prize winning work. Whether or not you will win one, let's see in the future. Okay, thank you.